Hello everyone, my name is Vimal Kakraparthi. I'm currently a PhD student in CS department at University of Colorado Boulder, co-advised by Dr. VP Nguyen of University of Texas Arlington. I'm here to present our system FaceSense, an ear-worn device that senses a face touch event and classifies whether the touch landed in a mucosal zone or a non-mucosal zone. This is a joint work between University of Colorado Boulder, University of Texas Arlington, Dartmouth College, and University of Oxford. The habit of face touch spreads pathogens associated with COVID-19, Ebola, influenza, etc. This involuntary habit is also associated with conditions such as chronic eye rubbing, compulsive skin picking, and several such obsessive behaviors, which have a lasting effect on a person's body. Existing devices assume hand-to-face proximity or specific hand motion patterns to be face touch. The innate problem with this approach is that there are numerous daily activities such as eating, drinking, adjusting glasses, taking a call, etc., that would be identified as a face touch. This leads to user mistrust of the model and an ineffective habit reversal. Ear-worn thermal cameras capture an approaching hand and spatial hints in a privacy-preserving manner. And physiological sensors capture skin deformations caused by face touch in the form of skin impedance changes. This information can be fused to identify a face touch event and classify whether the touch landed in a sensitive zone, such as eyes, ears, nose, or a non-sensitive zone of the face. We propose FaceSense, an ear-worn device that fuses data from thermal images and physiological signals to detect an actual touch and classify whether the touch landed in a sensitive zone or a non-sensitive zone. The first challenge in realizing such a system is that basic facial activities such as talking, drinking, eating, etc. cause skin impedance variations similar to face touch. Second challenge is that the existence of thermal objects in a background can ruin thermal profile of a hand. The third challenge is to design an algorithm that effectively fuses heterogeneous data from physiological subsystem and thermal subsystem to learn proper representations of a face touch event. Our device is designed to overcome all these challenges. FaceSense system is composed of three major components, namely the physiological subsystem, the thermal subsystem, and a multimodal neural network, which we call TouchNet. Physiological subsystem uses a bioamplifier at its center. Two channels of this bioamplifier are connected to mix channels to a small area near the ear, one on each side of the face. These surface electrode connections are designed to capture skin impedance fluctuations wherever the touch is happening on the face, irrespective of the intensity of the touch. Prior research found that facial activities tend to generate equal skin impedance changes and EMG on both sides of the face. However, face touch generates unequal skin impedance fluctuations on both sides of the face, and there is no facial EMG. This can be observed in figures showing cross-correlation scores of two channels while doing the activities by themselves and when the activity is compounded with face touch. Thermal subsystem identifies the presence of a hand, which not only provides spatial hints for touch zone identification, but also helps to identify face touch events when they occur along with asymmetrical facial activities. Thermal subsystem consists of two ear-mounted infrared thermal cameras that are low power and have a low resolution of 8 by 8 pixels. The subsystem has a field of view of 120 degrees, vertically and horizontally. We implement background subtraction followed by the binarization of thermal images to single out hand signatures from noisy backgrounds before feeding them to TouchNet. Next, we designed TouchNet, a multimodal deep learning model that is composed of three main modules. The feature extractor, which learns joint representation from heterogeneous data. the user discriminator that improves cross-user performance by suppressing user-dependent information, and the face touch detector that actually classifies the data. The implementation details of TouchNet are elaborated in our paper. FaceSense wearable consists of two flexible earpieces manufactured using thermoplastic urethane. These earpieces ensure contact quality of surface electrodes, positioning of thermal camera, social acceptability, and user comfort. The average cross-user accuracy of FaceSense with 14 participants is 84% with binary classification. Touch zone identification currently requires a small training overhead of 5 minutes for each participant to achieve a high macro F1 score of 90.8% and a micro accuracy of 90.1% with three classes, namely no touch, non-sensitive touch, sensitive touch. For more details about data analysis, evaluation, prototype implementation, future work, etc., be sure to check out our paper at UPConf 2021. Thank you very much.